installed. I'll write it down, but it's like this. If you Google that, you will see an installation page, and there are two options for Windows. One option is standalone, another option is OSGeo version. All kinds of good. But basically easy, you just download, and it says step by step what to do. First thing I upload, basically uploaded currently to my own GitHub because we didn't have time to be on his at some point as well. So you have on, if you look for this user at GitHub, I forked from Rust Scalable Data Science. So if you go to the Scalable Data Science folder, there is inside a folder called Gis DB. Okay, inside that I've put for you a DBC file for a notebook for Databricks, so it's a good idea to download it, then you will be able to follow me. So you go to this user on GitHub, you go to Scalable Data Science. Inside that there is a folder DB. Inside that should be something with /03. Have you found that? DB. Yeah, inside DB you have 360 in 525.03. So there you have a DBC file. You should have it. Ooh.
You have figured and abused it.
That's a nice thing. Let me have a look. Because there you have all the links and all the the DBC. So download that and upload it to Databricks, and then you can follow me basically with all the links and sites. Yeah. Also have this wow detection is because you're not signing it, you're signing it to currently. Yeah, I can show you more in more organized way. So basically, it's GitHub wizard.
The DBC.
Yeah. So basically, here you have the DBC somewhere.
So this is her fork of Scalable Data Science. So she hasn't made a pull request and I haven't accepted it, so you won't find it in my list.
But basically everything else is the same.
Yeah.
I will do that eventually.
Yeah, that's fine. Just it might be easiest to just go to your community edition and hit the publish link so they can just grab the HTML.
Yeah, if you want to do that, that's also kind of okay.
So you see this publish notebook, which is if you can physically meet me for the assignments. So then you can publish and it'll, so then copy paste that. And now I don't know, how do we share this to everyone? So let's see. So I could just throw it here, maybe. Oh crap! You didn't
no,
command copy that.
Uh-uh.
Okay, sorry. That's
But basically, if you just download from my GitHub the DBC and upload to Databricks, that should also work. So for those of you.
So yeah, this.
Or that.
Yeah. So.
So has everybody done that? Are you on Databricks looking at this notebook?
No, I get an error.
No, from URL it doesn't work. Yeah. For everybody? How fine. I can probably export it as HTML as well. And then put it on GitHub. For those for whom the DBC doesn't work, I can put HTML instead. Don't know if that will solve it or not, but let's try. So upload files. We thought will be all kinds of problems, but not this one.
Well, you kind of didn't do what you asked. So anyway, so I'm actually just updating the link right now. So. But Marina, you can just talk about other things like QGIS.
Okay, now you also no, you don't.
Marina, you can just talk about other things like QGIS.
Okay, now you also no, you don't. Now you should also have HTML there. So I'll basically start by just continuing. So try to install the QGIS. I'll start with kind of the talk, basically. So what we thought of doing today, John basically told you what is spatial analysis and why do we care, right? So he kind of gave you the bird view. And what we thought to do is that I will come and kind of start from the 101 basics, basically go back to what is the point and how does it work. And then you have kind of a picture from both sides. So this is what I will try to do. I'll try to show what is GIS and how does that work. So basically GIS in the page in Wikipedia basically says it's Geographic Information System. Some use it as a science. So there are some debates. Yeah, so basically the term describes any information system that integrates, stores, edits, analyzes, shares, and displays geographic information. So basically anything that has geography within is within Geographic Information System. And basically it can refer to technologies, to data, to software, to all kinds of things, processes, and methods. And as you can see, the page is quite long. I suggest you read it at some point. I don't think we have time to read all of this, but basically one of the more interesting parts here are spatial analysis with geographic information systems. And here you can see different methods and what it is applied for. So because today we'll go through the basics, we won't go through all of these, and maybe we'll show a few, but it's quite worth to dive into that. Okay, so this is what we will deal with. And basically what I want to start with is the history of GIS. And meanwhile, hopefully all of you sort out the opening of the Databricks thing and so on. And basically one more thing, while I'm talking, it would be a good idea to download QGIS at least, because it takes time until it goes down. So I'm talking, but below here you have the link to the QGIS software. So for those of you who Googled and didn't find or something like this, you can follow the link and set up. Basically, this is cell number 11. So if you look at that and below, you have the download page where you can download your own local version for your own software. And I show here step by step for Windows and Mac, which I tried, and for me that works on Windows 10 and on Mac Yosemite. So anything better than that should work as well. One thing with Mac, though, if you have Python 3, which is not 3.6, you might have some problems with QGIS 3. Then just download the previous version. It doesn't matter for today. So don't kind of get stuck on that. But I'll go back to why do we care, basically. So the birth of GIS, the first kind of first appearance of that was when when there was a cholera outbreak in London, and Dr. John Snow, not the same one, was basically looking at the cases of death and trying to figure out why, what happens. And he basically started the first GIS map. He started mapping the cases of disease, and basically each line here is another case. And then he figured out that this pump is basically the one to blame. So, and how did he do this? He basically mapped all these places, and in some kind of remote places, he still found cases that weren't explained. And then he asked them why, what happened, and apparently they were bringing water from these pumps. So this is how they figured out. And at the time, by the way, you can read all this story here, and Raz will go through some of it later, right? Because when you will talk about causality.
Yeah, so that's the Berkeley Data 8 course. That's the freshman level course, which we'll overload on.
Yeah, so basically this also will tell you the story of John Snow, but one of the things that was interesting at the time, there was this theory of miasmas, the smells, and they thought that cholera is transferred like that, but he was just mapping the cases, and from the map he figured out what happened. So this is the first kind of case of GIS. This is the original map, and the pump is kind of in the center, and what they did, they took out the handle, and apparently this way saved quite a lot of lives. So now it's even kind of a sentence in epidemiology, where is the handle of this pump? Which is kind of means how do we solve this specific problem? Okay, so that's the story. So this is why we map things. And one more kind of important part, which is why I was so stubborn about visualizations. The visualizations of maps are actually very important because they kind of half show us what will be a solution, but they need to be correct, because basically any visualization is subjective. We make a decision when we do this, and you'll see that in a few moments. So that's kind of the intro. And basically, when people talk about GIS, and Longley and Goodchild are kind of the fathers of the field. So this is a book, it's whatever, 5th edition, I think, or I don't know even which. So these are the parts of GIS that are included. And today I will show you a basic software and a basic kind of structure of the data and some of the procedures. So kind of you'll see a bit of the topic. One more thing that I'm showing here is what kind of applications could be done with that. But I think basically John showed you quite a lot today already. What we won't have time to do today is to talk about raster data. So basically this we won't touch, and it doesn't matter for you for the continuation at studying with Magellan, but kind of good idea to know that that exists. So in terms of kind of sorting out the GIS software, this is basically, in my opinion, slightly maybe outdated, maybe not, but what we'll do today, we'll look at the GIS software that is desktop-based, that is local, which basically means single node and non-scalable, usually, right? So then Raz will talk to you about the scalable options. There are several, but you'll learn one of them. So yeah. So in terms of GIS geographic information system software, as you can see, there is a list. Basically, today I was kind of wanting to stay with the open source free software. So we are going to work with QGIS, which is just one out of several. It's basically gaining support, and it's a big community of developers, which means it changes quite a lot. Sometimes it's glitchy, but next week it's not. So kind of keep up with the updates and so on. Which is kind of currently the biggest player on the free open source market. What you can also see here is that there are other tools, for instance, for web map servers, GeoServer, which we're looking at, and you have all kinds of others well, you'll see later. There are different types of database management systems, which PostGIS is just extension for Postgres, which is kind of it works with QGIS. I can show you a bit how, but maybe some of you will not be able to download the plugins to kind of work with it directly. There are different libraries. GDAL is already inside QGIS. Yeah, so that's about, yeah. And there are also the commercial kind of proprietary GIS software. The biggest player on the market is Esri, which basically have the ArcGIS software as kind of the mainstream software currently used by most of the agencies. But there are others as well. And well, I just kind of encourage you to read that maybe kind of slower, not really super important to focus on that. Just know that it's a huge world, and basically some of the tools are not even mentioned here, but I use them a lot. Some of them are good for one specific thing. For instance, Geoda is very good for geospatial statistics. So sometimes when I need that, I just use another software, which is supposed to be kind of cross-platform, but we'll see about that. And what we'll use today is free open source and cross-platform QGIS. And some people, actually, mostly researchers, also switch to R as a kind of GIS. It's not originally for that, as you know, but there are quite a lot of libraries, so some people just use it as a GIS tool. So yeah, and basically later you will learn with Rask about Magellan. So why Magellan? Apparently it performs better than the others according to Ram Sriharsha's presentation on Phos4G. But, well, Ras will talk about that. I'll leave this one to you as well. Why do we need one more geospatial analytics library? Let's just start. So what I'll do today is just kind of a crash course into what is GIS with QGIS. So let's set up. Basically, the example I'm showing here is based on the newest, freshest 3.02 Girona version, which I kind of tried to download and install yesterday on Mac and Windows again, and it worked for me, so like it's still okay. How many of you installed that already? Most of you, right? So is there somebody who didn't? And that's not, what is your, okay, so you're on what, on Linux or on? Yeah. So, okay, for Linux we have a Docker image, which I'm not sure. What's your using Mac? Yeah, for Mac I can help you. For Linux we have a specific Docker image, which the problem with it that we tried was that it can't connect to external resources, which for today doesn't matter, but yeah, so that's what I think. I can help.
She's on Mac. So.
Yeah. So for Mac, it's basically really kind of simple because on the download page, there is an installer for Mac, this one. And when you download this, you have different steps. You just have to follow the steps. For Windows, even simpler. Okay, so let's have a look and see, but that's good. So let's just start just by talking about basics until we kind of get to it. So after you install your version, which basically both for Windows and for Mac, I at some point opted into this OSGeo version setup, which means that you basically have several, it's really hard to solution, but basically what it installs it is version, and it also installs them. So if one of them doesn't work, you can always try the other one. But it also installs all the dependencies and several things that you might not want. But yeah. So let's start. Basically, what I want to do with you, the first thing is to just open fresh kind of QGIS page. So just kind of start a new and open a fresh window. And what I want to do with you, like this, is the first step is to do kind of hello world on QGIS, which is basically create a point. So what you can do, you can just kind of select this text, save it into your favorite text kind of edit, and then open it as a point. Okay, just kind of very simple, very basic. So I just select this text, I do Control-C, and I open whatever text wrangler or Atom, whatever you prefer, new file, and just save it as .txt or yeah, whatever. Once you have it, you basically go to your QGIS window and you want to open this text file. So this is something that basically enables you to open whatever data from other programs. For instance, you will see that you can do kind of summary tables in Databricks and Esri. Ras showed that last week. So then you can open them here and basically map them. So in QGIS 3, what they did, they basically united all the data input into this kind of open data manager. So for those of you who are using QGIS 3, just click on this button, and that basically enables you to open everything. For those of you who don't have QGIS 3 but still have QGIS 2.18, have different types of files separate. Is there anybody like that? There are several that told me that you don't have QGIS 3, right? Okay, so I can basically just open the previous one as well and show you the alternative version. So what we do, we just open a delimited text, and then basically QGIS will ask us, okay, so what is the X, what is the Y? And then it will map the point, right? So kind of QGIS 3 version, you choose delimited text, and then you have the X field and the Y field. So basically for the X field, or to find your file, right? So I open my file, and if you call your columns X and Y, that should automatically figure this out. But in my case, I called my columns lat and long. So it's a bit confusing that X is a long and Y is a lat. So it's if you are used to nautical navigation, it's the opposite: long first, lat second. Okay. And then another thing is it asks you in which coordinate system to work. For now, just leave it as a default. We'll talk about that later. In QGIS 2.18, it's almost the same. I'm just kind of showing you the same on QGIS 2.18. Basically, what you do, you don't find it, you create it. You just copy this text, open some text manager, like Atom or TextEdit, or you're on Mac, so you should have TextEdit. And save it as .txt or .csv or whatever. Right? So, yeah. Everybody okay with that part? Yeah? So just one thing for QGIS 218, it doesn't look the same. The input of the data, you basically directly click on this kind of picture of a comma instead. In QGIS 3, what they did, they united all the input into one thing. That's all the difference. Now, after we have all this, what you want to do is click OK, and it's out of bounds. Yeah. Maybe this way I can be able to do that. I never had this problem before.
Yeah, you want to increase the vertical from the top.
Yeah. It doesn't work. Yeah, I tried.
You can do this.
Oh,
that's all.
exactly.
Oh, there we go. There was a vertical one just popped up.
Okay, it's just a stupid problem because that, right? So just kind of click OK. And what you should see is just a point on your canvas, right? So it's somewhere in the middle of the void, floating a point, right? So have you all got to that part? STSV or .txt? Yeah.
Is the what is the is it an enter? Did you have to put an enter?
It's not. Yeah.
Crazy world. Like resolution bounds on how small the window can be. There we go.
So basically,
It's smaller, I think. So I don't know where you went.
well, it just went somewhere. So, okay, we have, Okay, I found
there
the
it
way.
says add now.
Yeah, I maximized the window. Genius. Yeah. Okay, so basically deleted file, we chose lat long, and then we press add and close. You should see a point, right? So basically this point is a temporary layer. It doesn't exist anywhere, it's just temporary depiction of the data. So if you want to send it to somewhere, you need to actually save it. So what I do is right click, save as, and then basically it gives you all kind of options to save the file. So what you could do, which is a bit weird but possible, is to save it back to comma-separated value. So you'll get back the same thing, right? But what you can also do if you do this, you can basically select in the options, the layer options, you can say, show me the geometry as well-known text, WKT, right? So you can do this. To give it some name, so just whatever, and save, and OK. And basically, the next thing that it asks us is, what is the coordinate system? I will explain you all this in a minute, but the default 4326 WGS84. And you click OK, and you should get another point on top of the previous one, which is basically the same thing, but in a different format. So let's have a look at what this basically means. So what we did, we added a point, right? So we added a point, and basically this point is a layer. In this case, it's a temporary layer. And all GIS systems, they keep their information in layers, usually. So this is just one of them. And basically, it's a good practice to divide layers by type. For instance, if you have a layer of water, a layer of points of interest or something, you don't mix them together. But you'll see later that we'll download some information from Openstreetmaps that is a bit mixed, which is kind of harder to deal with. So my first kind of way to deal with this kind of layers is to divide them by types, because this is kind of the better practice. So one of the things we can do also, we can save it as an Esri Shapefile. So I'll show you in a minute what it is. But basically, how do you do this? You just right-click your point, save as. And if you click here at the format, you can see that it gives you several options. So the options we'll look at is Esri Shapefile, comma-separated value, which includes the well-known text. And we will look at GeoJSON, because all three of those you can ingest into Magellan. So we'll look at them kind of with more attention. But you can have all kinds of other options as well. So just for the fun of it, I'll save it as a Esri Shapefile. And basically, you have to give it some name, and you do save. And you keep the CRS as it is for now and do OK. Now you should get another point on top of the previous two in a different format, right? So basically, this was kind of pretty simple. Look at what that actually all means. So in terms of options of formats, the first option we chose is Esri Shapefile. And it can give you several types of geometry. So basically, you can have points, you can have polylines or line strings, you can have polygons. There is something called geometry collection, which is kind of all kinds of things together. And it can be just a table without geometry, right? So it's a general kind of data frame, right? So which are basically the most common basic vector data structures in Esri shapefiles are points, polygons, and polylines. Esri shapefile, what you see is only the metadata, basically the attributes. You do not see the geometry itself. I mean, you see the point on the map, but you don't see kind of the encoding of the point. Right, so basically you have some table with IDs, and through these IDs, they are linked to geometry. But if you save it as GeoJSON, for instance, then you can also see the definition of geometry as one of the columns. Or another way, if you define geometry as well-known text, it's just another column that is geometry. Right, so you'll see it in a second, but the basic kind of the legacy format is shapefile, which is Esri format that is open source, and basically Magellan also uses it because most of the data that you can download, for instance, from the governmental agencies, are in shapefiles. So it's a good idea to know what they are. So basically what you did now, you saved this point as a shapefile. What exactly do we get? So if you look at the shapefile, this is the Wikipedia page of the shapefile. So basically, for instance, this legend has the well, the river, and the lake, which means it has three different layers of points, which are wells, of polylines, which are rivers, and of polygons, which are lakes. And it's a good practice to divide them, even though they're all kind of water. It's a good practice to divide them by type and also divide them by kind of what they mean, right? So this is just an example, but it's a good idea to kind of read through this. So the shapefile format basically is not one file. And if you look at your hard drive where you saved your point, you will see 6 different files. So this one point was actually saved as 6 different files, right? So some of the files, for instance, the shapefile, what it includes, it actually includes the geometry of the point itself. Okay, so it includes its location. The shapefile SHX, it's basically the index. The shape attribute format is a database kind of DBF format, which holds inside the table of all the attributes, and it links to the shape files using the index. And you also have different others, but these 3 are really needed. And there is another file that has to be there, which is .prg, which is the name of the projection. I will talk about this a bit later, but just so you kind of know. It's a good idea to read through this, to have a look what it is, because you will work with those shapefiles, so it's a good idea to know how they are built. I have here more links to the, So basically the shapefiles, they were developed by ESRI, which is the Environmental System Research Institute. It's an open source, it's the same kind of company that produces also the proprietary ArcGIS software, but the shapefiles themselves, the format is open source. If you click on one of those, no, that's the same Wikipedia page, but if you click on this one, what is a geospatial shapefile, you'll get to the original kind of document from 1998, since when we have this format. So it's a legacy format, it's a bit heavy. I will show you in a second how heavy it gets for just one point, just to compare, because there is a reason why we saved the same point in 3 different formats. So, but it would be a good idea to kind of read through that. It shows you what are the shapefiles, what are the technical kind of description of that. And if you want to ingest shapefile data, you might want to look at how it's organized and how to know how to parse it, right? So that's kind of the idea of that. Okay. And basically, both QGIS and Magellan build on ESRI library and the ESRI shapefiles, so it's a good idea to know them. And basically, if you look through a site of any municipality or Central Bureau of Statistics of Sweden, they offer you the data sets as shapefiles. Sometimes now they started to also share them as GeoJSON, but not as kind of common. So basically, to prep you for working with Magellan, we will look at the geometries and at the predicates that exist in both, but through the QGIS kind of framework. So we'll look at points, at polylines, which are line string, but that's kind of the same, polygons. What happens now that the new version of Magellan also supports multi-point and multi-polygon, you will see that in QGIS you actually don't really see the difference in terms of type, but there is a certain difference in format. If you want to know more, just go to README of Magellan, and we'll get to that later. So, right? But basically, we are talking now about the same formats that you will work with after lunch, right? So the basic main ones is ESRI, GeoJSON, and well-known format I will show you, OSM, XML. For that, you need plugins on QGIS. You can also open them, but I can't count on every one of you able to download plugins, so I try to kind of minimize that damage. So you have saved your point as a shapefile. Have a look at the size of all those shape files. And basically, if I listed them here, for instance, in my case, I have 6 files. The biggest one is 257 bytes, and the smallest one is just 5 bytes. And all of these are created when I saved my point as a shapefile. So if I look at the whole thing, and the original point in the CSV was just 24 bytes. So think about millions of points, how kind of it multiplies, right? And this is basically just 1 point. So in my case, this 1 point shapefile is 788 bytes, all the 6 files together, right? And this is in the original kind of WGS84 projection, right? So you already saved it as a CSV file with well-known text as geometry. Have a look at this file in your text editor. So in my case, I would just kind of go to where I saved it, which is, where did I save it? That's a good question. I think I saved it here. This one. So I just open it in my text editor, and what you can see that basically what it did, it added in the left another column called WKT, which is well-known format for geometry. So it basically added another column, which is the location information. So now if I want to import this point back, I can, basically I don't need X and Y anymore. What I need is only this one column, right? So this is the format for a point column of well-known text. Okay, it's pretty simple, right? So basically, if I go back to QGIS and import that file, which one? The QGIS3. So I go back and I now import the same CSV that I just saved, right? I exported it as well-known text. So if I do that now, what you can see that basically, if I think, no, I'm okay. If you look at geometry definition, it sees on its own that there is a column called WKT, and it basically doesn't need anything else. So this format is way smaller in size, but it's not as popular. But if you're trying to kind of keep your data smaller, maybe it's a good idea to keep it in this way. And I can just add it, so you'll get another point on top of all of those points. So then the last one is the one I just imported. Yeah.
Now when you save it, you got like an extra field. You included all the data from the other fields. Doesn't that make the size larger?
Yes, that's true.
That's like redundant.
In this case, yes, but basically, I will show you in a second that when we change our coordinate format, you might have X and Y in lat and long, for instance, and then well-known text in some other projection. Then it might not be, right? But basically, you are right. If you want to have it as slim as possible, you throw out the rest, and you stay with this one text kind of column. And as of all of the types that I tried here, this is basically the slimmest that worked for me. So what I can show you, for instance, that if you save it as a GeoJSON, and here, for instance, the WKT of our point is 76 bytes, and the original was, what was it, 45 or something? So yes, it's bigger a bit, but, and this is how the GeoJSON of the same point would look. So if you save it as a GeoJSON, you get basically type, feature collection, name, which is whatever name I gave it. Then you have the CRS. I'll talk about this in a second. That's the projection. It basically means in what language, longitude, latitude, or what kind of coordinates we're getting. And then it gives me the coordinates, basically, right? The Y and the X. And the geometry, type, point, coordinates. So this first part are basically the columns of attributes. Right? It's not the geometry. So you can change them, you can add them, you can, for instance, add another one as the, why did it jump? Sorry. Yeah, so basically what you can do, you can add to it as regular JSON, just another column. Then if you put it back, you understand, right? So basically, yeah. So now this part, the CRS, what does that actually mean? Until now, you just accepted the coordinates X and Y without kind of questioning what they are. So what we got until now is lat and long, which is easting first, northing later, in degrees, decimal degrees, just like in Google Maps, right? But basically that means that if you measure distances or if you calculate distances, they will be in what degrees? So it's kind of, right? So this projection, it's good to make maps, but it's not really easy to make calculations and make basically analytic. Yeah. So what we want to do, we want to basically know in which coordinate system we are working. So the CRS that you saw, it defines basically the datum, the reference surface, and the projection. All of them together have a code number, CRS, which is Spatial Reference System, I think, Coordinate Reference System. You have all kinds of names for that, but the story is basically how do we translate the Earth to X and Y coordinates, right? So, and it's not flat, so it's a bit of a problem. So how do we do this? And whatever we do, we always have some kind of distortion. And basically, what we do, we kind of from the Earth's surface, we approximate to a geoid form, which is kind of like a potato. Then from that to an ellipsoid form, which is from that to spheroid form. So there are all, for each of the transformations, you have a formula which kind of has a code. And this code is in the, basically in the CRS system. So I hope this image kind of illustrates that more easily. The thing is that WGS84, the projection that you have seen until now, it's good globally, or let's say it's equally bad everywhere, or not equally, but kind of the same, right? So you can make a map of the whole world and you with minimal general error. But if you want to depict some location very precisely, say this university, you might want to have a projection that locally is more accurate here in Sweden, but will be not accurate somewhere else, right? So you just look for a surface that approximates better here, right? So what we basically will have to do, we have to look at all those surfaces, and in this case, what you have different types of projections. So WGS84 is basically a projection. It's not a projected, it's a geographic coordinate system, which means you kind of always think on a globe, not as a flat surface, right? But what you can do, you can project the globe to the flat surface in different ways. The most common is the Mercator projection, right? And then you treat your coordinate system as if it was flat. And then the units that you have can be metric or feet. And basically they approximate locally. And yeah, so how does this work? The projection I'll show you today for this specific area is 3006, which is VRF99. It's the kind of most common in Swedish data sets. Basically, it's universal transverse, it's UTM, the Mercator projection. What they basically did, I'm looking for an image for that. What they basically did, they took a globe, right? And then what you can do with the globe, you can kind of put a page of paper around it, right? Put inside the light and kind of project outside, right? You understand this kind of picture? I had an image for that, but kind of the simplest Mercator projection was like this, right? So you take the globe, you put inside the light, you kind of put a cylinder around it and project everything outside, right? So what you have more distortion towards the poles. The universal transverse Mercator, what they do basically, what you can do instead, you can put this horizontally, so it touches one of the meridians. So near that meridian, you will be very precise, right? Then you can do this again and again for each zone and kind of stitch it together, right? So for each specific zone, this specific projection will be correct. For the next zone, you will need the next projection. So this is, for instance, this projection that I will show you, the 3006. Or for instance, this one is the local projected coordinate system, which kind of thinks as a flat surface. Am I making sense? I hope. Okay, so if you want to read more about that, there is basically quite a lot of links here. So one of the links that is worth following is what is a spatial reference system. This is basically just the code for this projection. SRS or CRS coordinate reference system, they usually have numbers, like WGS84 has 4362. I'll show you in a second. But basically here you can read all about this, all these kind of types of projections, the identifiers, and how does all that work. For instance, NAD27, it's the UTM for United States, North American datum, and so on, right? And they also have the EPSG number by which you can identify them. WGS84, this is the projection we just used, which is basically not a projection. It's a geographic system, so it's in degrees, right? The problem with degrees is what? That basically if you go up and down, north and south, they are the same degrees. But if you go east and west, basically the distortion changes towards the poles, right? So degrees, for instance, diagonally don't really make sense, right? Or degrees horizontally are not the same degrees as vertically. So this is a problem. This is why we basically work a lot in projected coordinate systems, even though you can't depict the whole world with them, right? So that's kind of the idea. But if you want to read more, and I strongly suggest you read some of this here, just to kind of understand the whole picture. Another link that I've put here, somewhere here, is this one. It's called specialreference.org. That should work. Maybe www, yeah. Okay, so this is the site that basically includes all the major special reference systems. So if you are not sure, for instance, you will be working with the New York dataset and with San Francisco dataset. If you are not sure which one to pick, you just go to this page, look up different special reference systems, and you can see which ones of them are valid where. For instance, the one we used is 4326. This is the WGS84. So if you click on that, it will tell you everything about it. It will show you the picture in this projection. It will show you where is the origin, where is the zero kind of, right? It will also produce for you, for instance, the .prg file if you want, or it will produce for you the JSON. For instance, the JSON for WGS84 is just very simple, one line. This is why the GeoJSON was so small. But if you choose some local projection, you'll see that the GeoJSON files increase. Is that clear? I'm not sure if that's clear or not. The moment you use the standard projections, the JSON file is just the code. The moment you use some more complicated projection, you get a longer string that basically increases the size of the file. I hope this is kind of easier to see. But here you can kind of look up any projections. So for instance, 3006, which is the Zverev 99, which is most of the Swedish data sets that you get now from the government are in this projection. So you can see what are the bounds. The bounds are basically between which latitude and longitude it makes sense to look in this projection, because outside of that, it's not accurate anymore.
I get an error when I look at the JSON for this one, 3006. Okay, so there's something here. Okay.
Yeah, it's this site sometimes, especially if a lot of people go there, it glitches sometimes. But in this case, it's a standard projection. So basically, you just have EPSG, which is just the name of the thing, properties, code 3006, that's it. Most of the GIS systems know how to parse it. But you basically can write your own projection if you want, right? So, yeah, so you can also look at the human readable text, which can tell you all kinds of things. What is the zero, what is the unit, which authority, what is the kind of, what is the type of the projection, the origin. By the way, here you have other parameters, for instance, false easting and false northing. So in some of the projections, you basically measure in meters, but you add some kind of number of meters. It's done so you don't have negative numbers, so it's easier to calculate within the same country. So you will see when we kind of convert to the Swedish 3006, you will see long numbers of kind of bigger integers, which are in meters, basically. And you'll see kind of thousands of meters, and none of them become negative because of this false easting or false northing. So in case of Sweden, you can see that the Sverige 99 has the false easting of 500,000 meters. Okay, and the false northing is 0. So I hope this kind of makes maybe some order in the question of what is the projection, because this is, even with our own students, sometimes they kind of come up with this mystery, what's the projection and how that works. So if it's not clear, please just read these files and look through them. It's important because basically anything you do with geospatial data, for instance, if you measure area, what projection affects the result? If you put layers one on top of the other and there are different projections, you're likely to have some kind of mismatch even between the same data, right? Between something that is supposed to fall exactly in the same place. And another thing is, whatever projection you choose, it's always distorted. There is no way to show it accurately. So the only way you can think of it is just be aware of the limitations and take it into account. And it depends how much of the precision you actually need in your results, right? So if you really want to know where the parcel stops and the other one ends because you have a dispute between neighbors, it's one thing. But if you want to see population density on the community level, maybe that doesn't matter, right? So that's kind of thing to consider. But again, if you kind of are interested or at some point you get this question, just go to these links and read that through. Usually most GIS systems, what they can do, they can apply transformations from one system to another. In terms of QGIS, it's basically a click of a button. In, for instance, Postgres, it's just you kind of write a query in that way that it translates, so there is an inbuilt function. But if you need some kind of specific transformation that is not built in, you can also decode it by just going to this one, reading that through for both of the projections, the one you go from and the one you go to, because each of them have the datum, the formula of how to basically approximate the surface, and the false easting, false northing, and so on. So once you have both of them, you can kind of translate from one to the other. Raz will show you, you have it in one of the codes, I think for New York. You'll see it later. But basically in one of your later kind of examples, you will see this formula of how to do the conversion.
Yeah, we'll do all the arithmetic from scratch, right? Every month.
Yeah. Yeah, so when you get to just have a look, because it takes a while to figure out how to do this. It's not really kind of simple, right? But in our case, in QGIS, what you basically just do with your, say, whatever, which one of them, I usually just use a shapefile because it's kind of less glitchy. So the first thing I do, I choose the shapefile and I save it as a shapefile. So what I do now, I just give it some name, for instance, 0.3006. I want to save it as a shapefile, and in this case, I want to project it to another projection. So all I need to do is just change the projection. And you can see that it offers me projected to something else. In my case, it remembers what I already tried. In your case, what you can do is click that. It gives you all the options. If you know the ID of your spatial reference, you just write it like 3006. At this point, I know this by heart, but if you don't, just look it up first. And basically, usually the municipalities have on their page where they put the data, they have this part, for instance, Uppsala Kommun has it somewhere, like in what kind of SRID they offer their data. Right, so in our case, most of the data comes in 3006. A neat thing in QGIS3 is that they added this map. This little map shows you where this projection is valid. So it kind of half solves for you the problem. But basically, if you don't have it, if you have an older version, just go back to this SRID page and have a look. And what you can see here is basically the calculation itself. Right, so it has the what kind of surface you have, ellipsoid or spheroid or what, and it has some of those surfaces have this code, so sometimes it's just enough to give the name of the code. You have the extent, you have basically from what to what and to which units and so on. So our units are meters, zone is 33, don't really know, yes, I actually know what it means. I'll kind of can show you. But what you basically do is just select this and click OK. And click OK, and you should get a new point in the new coordinate system. I have to say that, yeah, sometimes it's glitchy. So in this case, it's glitchy for me. I hope for you it's not. In the old system, that doesn't happen, but sometimes in this one it does still. But theoretically, to reproject some file, you just right-click, save as, change the projection, and that should work. When it does work, when you right-click and open attribute table, which is basically take a look at the attributes of this file, you should see a row here. So if there are no rows, something glitched. So in this case, it did. If you look at the original point, you can see that it has ID number 1, latitude, longitude, 0.1, right? So I don't know why, but yesterday I spent quite a lot of time trying to figure out why it glitches. The same point into Utm doesn't glitch, so just ignore it for now. Right, so let's continue. But do you have any questions on SRID or how that works? Or is that clear? Kind of, I hope. Because it's not the most kind of fascinating topic, but basically all your analysis depends on this. So the projection, it's a good idea to get it right. Okay, so that's kind of the idea. Okay, so if we go back to our point, and I basically here just show you the steps of how to do this, of what I just shown you. And if you have a look at the shapefiles, in this case, it didn't glitch for me, but what you can see that some of them are bigger. So in my case, they were almost double the size, some of them. Which is kind of weird because it's the same information, just in a different projection. So if any file should be bigger, it's just the .prg, right? The one that shows the projection itself. I really don't understand why it should be. I mean, one of the reasons maybe that the length of the string is longer because you have more numbers. It's in thousands of meters instead of just, you know, but still, I mean, double the size. So just to show you the differences, basically I show you here several types of files. So the shape files, the GeoJSON file, and the well-known text. And I basically also show you how it looks, the well-known text. So this is WGS84, the geographic system in decimal degrees. And this is the serif system in meters. So what you can see, for instance, here, that you get 600,000 meters east and 6,600,000 meters north. So these are the units. But basically, if I add one more, I just added one metric meter. So you can actually use these coordinates and calculate distances on them and so on, as if it, well, not, if the distances are small, as if it's flat. Okay? But if you look at the sizes, the WKT is bigger. the GeoJSON is bigger, but the shapefiles are really like considerably bigger just for one small point. So just kind of to remember as, yeah. And if I look at the .prg files themselves, it's a text file that you can open and have a look. So for each of the shape files, when you save something as a shapefile, it creates a .prg file which you can open in a text editor and have a look at that, especially if you want to decode how it translates from one SRID to another. So it shows you here all kind of information, what kind of surface it is. This is the spheroid of this one. Yeah, this way you can at least see that. So you have the scale factor, you have the false listing, you have all this information here, right? So once you save as a shapefile, it's a good idea to open the PRG and have a look. Now, another thing is datum. Basically, datum is a group of points which are reference points that basically used to reference the surface to the actual surface of the Earth. So there are kind of like control points, right? And basically, for instance, you will use the North American NAD 83, which has a different datum from, say, 3006. So each time you kind of have to have a look. And false northing and false easting will be different for each different system. Yeah. Now let's have a look, for instance, what you do with, like if you want to add multiple points. Just kind of copy paste this text and create the CSV file the same way we did before. So what I do, I just copy that, open my text editor, new file, paste that, save it as a CSV somewhere, or as a text, and open that in QGIS. And what it should create for you, this is the older version. So again, I click on Add Data, delimit it, and just add this file. So we have lat and long. Again, I have to tell it that basically the X field is long and the Y field is lat. And add. And you have a group of points, right? So basically, if you right-click that thing and open an attribute table, you get the same latitudes and longitudes of these points. Now, I hope that won't glitch if you basically save it in a different SRID. Let's try and do that. So basically what I do is right-click that, save as, and save it in 3006. The same file, I just save it as a different system. Did that glitch? No, that did not. So basically now, what you have is points in different coordinate system, but it still remembers the lat and long from the previous one. What if you want to get back the coordinates of each of the points? You can basically create additional columns. You can measure geometric kind of metrics of, for instance, if I want to know what is the X and the Y of the new points, what you can do is create a column. So what you do is just open field calculator, and I call this one X, and it has to be double. Have you, I don't know if you've seen where I clicked, it looks like this one.
Which file did you open now? The shapefile or the CSV file?
Basically, it's the shapefile. So I have this shapefile that I just saved, right-click, open at your table. Here you can calculate all kinds of things. So for instance, what I want to do, I want to know what is the X in meters of these points. So what I can do, I can open the field calculator. This should be the same in all versions of QGIS. I create a new field, call it X, and put here $X. And okay. Now what you have is the metric, basically value of this X. So you can always kind of retrieve this data, but in a shapefile it's not visible. Is that clear what I did?
I only have, I just managed to write this, but I see nothing.
So right click that, zoom to layer, zoom at your layer, the top one. Exactly. I skip that part. Everybody's, yeah. Okay, so if you want to see some layer, you can always zoom to it to have a look. Okay? Questions? More questions? Yeah, what? Yeah, open up to this page. Yeah. Okay, what else do I want to show you? I kind of need to continue. Yeah, so basically what I can also do with that, I can I can edit the layers. So basically when you add another column, you're in the edit mode. When you finish with your editing, you need to toggle and save, right? So every time you change something about the layer, you open it in the edit mode. So you cannot save it in that position. So once you're finished, you have to close and save. Yeah. So this is basically how you add different points. Now, if I save the same points, I don't want to do that with you because you already saw how to do this. But if I save as CSV with well-known text, how that would look. So if that's the case, what happens with polygons? So basically for polygons, I'm showing you here one example of a polygon. So basically if you kind of just take this text, which includes well-known text for, in my case, it didn't work. That this text, right? So copy, again, the same, create new CSV file, save it, and open it in QGIS. So basically we add new file, delimited text file. With the difference that basically now it figures out on its own that it's a well-known text, that's a polygon type. You add it and close. And then if you want to see the whole polygon, right-click, zoom to layer. Now it kind of looks a bit strange. So if you want to change the way it looks, if you want to reproject it to be correct, currently what it does, it shows me my whole map as WGS84. So basically, besides each of the files, you have also the projection of the map itself. So my current projection is this one, 4326. So that's the code of the regular WGS84 projection. So if I click on that, I can reproject everything I see into a different projection. So let's just do that for 3006. And just click OK. And you see that the form of the polygon changed because it was basically reprojected to a flat projection. Currently, it's kind of hard for you to probably see what that did, but you'll see in a second why that matters. Now, if I save it as GeoJSON, let's kind of not do it, just have a look at how that looks. Basically, this is how GeoJSON of the polygon looks. What you have, you have tuples of points. Each of them is x, y. And you have the list of points in order. And if you pay attention, you see that the last one is the same one as the first one. So basically, to show that the polygon is closed. If you look at the well-known text, you'll see that as well. The first point is 17.6453, and the last one is the same. Okay, so have a look at the well-known text. Basically, what it has list of points, and then the last point is repeated again. The first point is repeated in the end to show that it's closed. Is that clear? Right, so this is basically very similar to the format that Magellan has later. You'll recognize this. And in Magellan, basically, the polygons work slightly differently because, like in the way it's written, but basically it's the same. You have a list of points. The first one is always repeated in the end. What they also have, they have this special format for holes. So currently you have here an empty array in the first place, but if you look in the second example, you have a hole. And basically this hole, the 0 and the 5 says that from the 5th position, the points describe the hole, not the main polygon, right? So this is kind of the format that, so you recognize it's almost like the well-known text. It's almost, they kind of all make sense in a way, right? So how would the polyline look? This is an example of a polyline. I'm kind of skipping it to show you the next stuff, but if you kind of look at the well-known text of a polyline, you can see that that's multi-line string, which basically doesn't have to close, but if you add the first point in the end, it will close. It doesn't really matter. It will still not have this property of area. If you open the polygon you have in your QGIS, right-click and open attribute table. As of now, it only has the GID. But what you can do, you can calculate for it the perimeter, the area, and all kinds of other things. For instance, you can calculate the centroid of the polygon. Right, so all of these are built in. Yeah, so I'll skip on, but basically it's the same as you did with the X. You do $area and it calculates the area for you. With one little caveat, if you are now in the coordinate system that is in degrees, you might want to switch first to 1 meters. Okay? So, I'll skip the creating geometry for, basically, no, I want to show you one of them. Say we have this polygon. What we want to do is create a new type of geometry. There are several ways to do that. Way number one is to just create a new geometry. You have this new shapefile layer. Basically, you just click on it, give it some name, and start clicking to create one, right? So I'll skip that for now, but you could do that. I would say more interesting way to do this is to basically do that meaningfully. So what you have in QGIS 3, which you do not have in QGIS 2, in the bottom part, you have the search window. So if you know about some kind of command that you don't know where to find, you can just start looking. So for instance, let's look for buffer. And just click that. What buffer does, it basically offsets a polygon for a specific distance. What this in what units? How do we know? Basically, in our case, we're currently in 3006, so it will think in meters because my map is in meters, right? So if I want to offset my polygon by, say, 20 meters, and I zoom. Why didn't it work? What do you think? It looks weird, right? It doesn't look like a polygon. Why didn't it work? The original polygon was in WGS 84 in degrees. So when I told it offset by 20, it offset by 20 degrees. So before doing that, you have to project the polygon, right? But basically, if I do this, I just right-click, save as, save this as 3006. And save it. Now I have my polygon as in meters. If I do the same operation again, the buffer, but now to my new polygon, what you have is 10 meters. As you can see, just offset it by 10 meters. So when you do this kind of operations, be careful with what units you're working. Now, one more thing, because I'm kind of short in time, because I dig deep into your brains with the projections, which currently is a bit of my obsession, but I think it's important. I still want to show you some predicates. So let's just skip the drawing geometry. If you want to, you can always follow this. Basically, there are different ways of creating new geometry. The types that might be interesting for you is to repeat the buffer again to have a look what it does, and to look at the bounding box, because you might kind of use it in computations. I'll skip the other ones just for the sake of time. Now, you can run simple queries. I'll skip that as well for now, but it's basically like doing SQL, but through GUI. And basically, if you want to do SQL, you can connect to PostGIS and run PostgreSQL inside QGIS. I'm not going to show you now because it involves installing plugins, but you can do that. It's not really a problem. But what I want to show you is basically the spatial predicates. So from Esri, what we have is kind of this, how do you say, the language of the geometry. So what you have for points, you just have the points themselves. So basically, they don't have boundary, they only have interior, right? For polylines, you have basically the boundary, you don't have an interior, but you have the ends, the points. And for polygons, you have nodes, you have the interior, the area, and you have the boundary. Now, all the predicates in Esri basically are defined from these concepts. So for instance, if you look at the intersect, right? So intersect basically means that if any part of one of the elements touches another one, right? So then it's intersect. Contains means basically if the points are contained in the polygon. And within means the opposite, right? So if these points are within the opposite, so it's basically, yeah. So in QGIS, you also have several others. For instance, what you have is that equal, which means all parts are the same. So if you have polyline and polygon that follow the same lines, they are not the same, right? Because you have to have the boundary, the area, and the points. The disjoint means all parts are different, basically, and you have several others, touch, overlap, cross, and so on. So what I would like to show you is just the 3 types of predicates in the last kind of 4 minutes. And I encourage you to look further, because like it's just, I kind of tried to put in what we teach in a semester in more or less an hour and a half. So I hope that you guys kind of sit with it, play with it a bit to figure out how that works. But this part is kind of important. So let's have a look, for instance, at these 3 predicates: within, contains, and intersects. All of them are basically in QGIS 3, sit in the same vector analysis, I think. No? They changed the... I forgot where that sits. But I think, yeah, vector selection. So basically what you do when you do these predicates, you select by location. So in other software such as ArcGIS, you just have select by location as a kind of a command. Here you have extract by location. which is basically the same thing. So let's just zoom in to have a look. One of the predicates that I can look at is within is the green polygon within the yellow one, right? So what I can do is extract by location. The green polygon is called R something. So what I want to do is extract features from, or maybe let's look at the points because it's more interesting. Are all the blue points inside the green polygon, for instance, right? So if I want to know this, I click on extract by polygon. I select features from points. Which ones? I basically don't know which ones are those. The ones that are called E, whatever these ones. And I want to know if they sit inside the polygon, the green one, which is called R3006. So basically what you do by extract by location, you choose from, you choose inner join to, right? And then you choose by what kind of Boolean returning function you join them. So for instance, in this case, I want to know if they are within. And I run this, and basically if they are, it will extract the points that are within. So if I make these points big and purple, you will see them. If I just make them bigger in size, you see all of the points basically fell inside, so it extracted all of them. To understand what it did, I basically tried to write for each of them. So for within, for instance, I wrote for you the PostgreSQL query that is basically what it does on the background. So it selects all from the layer points as, say, as a inner join to my polygons on within, which is the function that returns Boolean, yes or no. If yes, keep, if no, throw out, right? So this is kind of how it thinks. So it kind of is written here inner join, but it's misleading because what it does cross join, like Cartesian join, basically joins all of them, then throws out the ones that are unnecessary. Whereas we'll talk about that because in Magellan there is a way to make it faster, with spatial joins, right? But basically what contains does, it does kind of the opposite. Select star from polygons, inner join points, on contains, right? Does this polygon contain them or not? And with intersect, basically same thing, but you can intersect polygons or points in polygons or lines in polygons and so on. Basically, if any part overlaps any other part, it intersects. And if they are all inside, that also intersects. Is that part more or less clear? Because everything else you can more or less go through on your own, have a look, but I think that was the kind of the important basics. I mean, I had some more stuff there.
So do you have the Openstreetmap upstairs? Or?
Yeah.
Could you quickly show them that? Because that's crucial for...
Yeah, so I'll skip the scaling part because you're talking about that, right?
Yeah.
Okay. So besides the predicates, I'll skip that. But basically, I'm talking about ingesting data from Openstreetmap. And there are basically two ways to get data. The first way is raw data, which is .osm format. It's kind of a database format that to read that in QGIS, you need a plugin, which in my case was just one click. And then you can run queries on that database. Another way is to get it as shapefiles, which is, I'm basically showing you both versions. So version 1, from one of the sites that basically what these sites do, this one, extract bbbbyte.org, what they do, they connect to OSM, translate their database into whatever format you want, and give it back to you. So you select some area, and you basically give your email, click extract, and it sends it to you. With this specific version, which I encourage you to follow and open this in QGIS just to see what you get, what I got for Uppsala is not all of the elements. So basically, this BBB bank site, they extract, but not all of the information. And they transform it somehow, so like you basically don't know how, you just got some product, but you can't be really like sure if you got everything. And basically, I'm showing you here later that at some point I'm showing you that on top of an OpenStreetMap, and you can see that not all the elements came through. But basically, what you get inside this OpenStreetMap, you get different features, basically points, polygons, and polylines of different kinds. And if you are interested in what specific features you get or which ones do you need, you have to go to the wiki page of OpenStreetMap. It has a very accurate documentation of all the shapefiles that are there. And basically, they have their own encoding of the types of the elements that are inside. For instance, amenity, which are usually come as points or as polygons. So as points, you have a point, you have amenity, for instance, cafe. Then you have attributes, say name, okay, and you can have other things as well, like hours or website or whatever, right? So, for instance, if you want to see, for instance, amenity education, so you have different types, and they give you here all the types. So basically, you can get into each of them and have a look what that means. So when you have your data set of points from OpenStreetMap, you can kind of have a look which ones of those you need. Say, for instance, I choose university, and then they will kind of show you what they mean by that specific one, right? So this is what points get this tag, amenity equals university. What does that mean from OpenStreetMap point of view? So when you run queries on this data set, it makes a good sense to have a look at this documentation. For instance, one of the things that is important to check, if you are downloading roads, they are called ways, and there are different types of encoding for roads. So you can have bicycle ways and you can have pathways, and sometimes they kind of overlap because basically they're on the same road. So it's a good idea to have a look. Yeah, I have to go back one more. So you have buildings, you have highways, for instance. Let's have a look at that just to kind of. Yeah, so for highways, for instance, you have the key highway, and then you have different values of the key highway. So you have a column called highway, and basically it can have not now, then you know that this thing is a highway. So you can select all roads with the column highway that is not now, right? So you already got all the roads, and then inside the roads you have the types, motorway, trunk, primary, secondary, etc.
If I made a key point about OpenStreetMap, it's not formatted into citizens movement, unlike the Google or Apple formats. This is so you can make a business model out of it. Yeah,
and basically the nice thing is that they are very kind of organized in terms of standardization of the text. So some text might be missing, but the ones that are there are according to this specific format. So this is kind of nice. You won't get just HUA. It's highway and it's supposed to be spelled correctly and so on. Right, so, but even so, the last time I downloaded this, I got the invalid geometry. So when you download, you usually get some points with zeros or some points with null coordinates and so on. Last thing.
Could you show us quickly how to open?
Well, basically, in this case, what I did is just download the shapefiles and then I opened them regularly. But if you download the plugin, you can open the .osm and basically query that. So this I can show you. Most of you, the ones that are not with Linux for sure can do that. The ones with Linux, let's try. I can't promise that will work. But basically what you can do, you go to plugins, manage and install plugins, and basically click OSM. A lot of things come up, but basically Quick Map Services, what it does, it basically gives you the layer of the picture behind your map of OpenStreetMap data. So it's kind of tiling of raster. It's nice to have as a background. But basically what you want to do if you want to have your data, you want to download it on your own computer mostly, right? So basically, in this case, what you might want to have is Quick OSM. So the plugin I'm suggesting, this one is a new one, just has been updated, but it actually works in the older system as well, is Quick OSM. So you go there, you click here. If it's not installed, it will say install plugin. So just install the thing and close. And you will get this icon, Quick OSM. So if you, for instance, click on that, and I just zoom out a bit and turn off the 20-degree thing. Basically, when you click on that, you get this Quick OSM query. So it connects directly to the data set, and you can query the data set directly without downloading all of that. Okay, so 2 minutes.
You can start a little later.
Okay, so basically, for instance, here, if I just select the key building and the value, yes. So I want something that is a building. I don't care what it is. I want to know that that's a building. As you can see, it will download not all of the buildings, because if it says building equals whatever school, it won't download it, right? But now I can just, and basically what it does, it answers select star from Openstreetmap where key building equals yes, in which area. So here you can basically select extent of the map canvas, which is what I currently see on my screen, whatever I zoomed into. What you can do instead, you can select some shapefile. You can, for instance, draw a polygon and say, take this one and take its boundaries and look there, which is what I usually do because I want to be precise in what area I'm looking, right? So you can write a well-known text for your polygon, then open it, then tell this thing, look at this polygon, take all the data inside this polygon, right? So in this case, I'm just going to extent of the map canvas, run query. And as you can see, it's downloading, parsing, it does all kinds of things. And in the end, what it should do, it should just add a layer here, or maybe several, because that basically depends which layers have this key building. So it could be polygons and it could be points. In this case, it should give me polygons. So let me show you what we've got. And we've got basically buildings of Uppsala. And this point that I was kind of torturing you with is basically here in Anstrom lab, right? So this is the building. I was hoping to get to that, but basically this is kind of how you can use it directly just by querying. So you can do that for instance, key highway value, I don't know, secondary, and download all the secondary roads. So this is one of the ways to do that. There are several others. Basically, all of those plugins, what they do, they basically use the API of OpenStreetMap. They're all written, most of them are written in Python 3 in this case. So you can write your own if you want to basically download it differently. Now, I also added to this notebook, this is kind of the last point just to kind of show you. There are all kinds of examples, but in that I also added for you how to download the OpenStreetMap data for Magellan. So you can go back to that if you want later, but what you basically do, you just do wget, and you get the whole .osm database within the boundaries that you save. So it's, in a way, it's better because you just get all the information raw, and then you decide which one you choose, right? So in QGIS, all the plugins, they kind of design it for you. So you design the query and so on, you get just the parts. So you guys decide what you want from that, right? But basically, in this case, what you do is just wget, give it some name, and then basically from this API, and these ones, L, B, R, and T are lower, left, bottom, right, and top boundaries of my query area. So what I did before, I just said I zoomed into some area, take this area, and give me the data from there. When you do wget, you just give the numbers in decimal degrees in WGS84 coordinate system, which is the native system for OpenStreetMap. That's why we spend so much time playing with that. So basically L, longitude on the left boundary and so on. So here is an example, for instance. We took center of Uppsala. I think it already sits in the data bricks. So what we took is 17.6 degrees left boundary, 17.64 degrees right boundary, and this bottom and top. So you have this kind of rectangle. And then you just you get that. We gave it the name tiny Uppsala centrum w.osm. So .osm inside has the shapefiles, but it's basically a database that contains them, the polygons, the points, and the polylines with different keys and different values. I don't know, is that clear? Kind of, yeah, because you're going to use that. Questions? Was it too easy, too hard?
One semester in 90 minutes.
Well, John just did the whole, basically the whole field in an hour and a half. So, yeah, but do you see what GIS kind of does? Because that was the main point. Obviously, it's a big field and you can dive deep into whatever, wherever. I suggest you go through this notebook. It has several more exercises. So if you go one by one slowly, you will kind of remember or re-remember or understand what I skipped over and such. And this is a good start. But what I also did here in the beginning, I mentioned several places where you can basically train. Where was that? Yeah. So basically, there is this guy, Ujjwal Gandhi, that wrote a really, really good QGIS tutorials, which were based on the version 2. So they're slightly outdated, but they're still worth following. So if you really want to learn GIS, or just a bit, it can take you, I don't know, 2 weeks. Depends how persistent you are to just follow his basic tutorials, and then you'll know enough to play around and make maps and so on. Okay, the parts that I didn't get to, which are basically the spatial analysis itself, contain basically all these steps in spatial analysis contain these things that we already did. How to make a shapefile, how to ingest data, how to do different predicates, and some of the algorithms contain them one after another in a list of steps, but the basics, the alphabet, I hope you have at this point.
And the main problem is you want to do these SQL, say, points within polygons to, like, say, hundreds of terabytes. Then the current systems, the non-distributed systems, don't work. So that's what we will cover. So,
yeah, basically I used QGIS with PostGIS in a project I was doing for like looking at policemen in Dallas. So I had locations of GPS, 6 million rows per month. And QGIS kind of could show that. It took a long while, so you click and then you go away and you come back. So basically I did all the analysis in PostGIS, and just to visualize the results, I opened them in QGIS. So this is kind of almost over the limit.
And when you scale up, are you leaving QGIS and use other tools instead, or?
Yeah,
that's the plan probably for tomorrow. So we'll do distributed geospatial analytics.
exactly. And like my experience was to work in basically PostGIS locally on this one node. But the thing is, you don't visualize, so a lot of energy goes into showing this. Like every step you do, it renders that. So basically, in the new QGIS, you can tell it, please don't render, please do it on the background and so on. But still, it's not as scalable as basically running it pure. So what I was doing was running it from the terminal, command prompt, so no GUI, whatever. I don't want anything that takes memory. And even so, some of my code might be not very good, but still, I guess some of the things took too long. And it was just 6 million. For instance, if I have 6 million rows for location of policemen and say 300,000 locations of crime, and I want to join those two. Okay, so yeah. Yes.
Yeah, and also, like, even if you do the distributed stuff to make a presentation to your bosses, you will want something snazzy like this. Otherwise, no one will care, right? The managers are not going to care. This is extremely important.
Yeah, we didn't have time to play with visualizations, but basically, Ujjwal Gandhi has a nice tutorial about how to make pretty maps. QGIS is amazing in terms of visualization because basically you can code everything. You can write a formula for the color that is derived from your attributes and so on. So you basically can create amazing visualizations just by clicking. And well, you can of course write JavaScript. Yeah. So, but I mainly use it as a tool to show what I've got and to look at the data. So every now and then what I did was just open in PostGIS, select a sample, and then just open it in QGIS. Yeah, that's...
Okay, so let's thank Marina and John. So should we start 20 minutes later? You guys want to have lunch break? I will just crash load you on distributed linear, but it's fine. So let's just take a look. So we'll just meet like 20 minutes later, right? So 1.5 hours. And it's in IT as well, ITC, it's across the board. It's across the board. Okay. Maze map also.
It's more like
Hey guys, I was thinking we could have like a talk about the master thesis.
Okay, so lunch I'm busy because I have